Hello everyone, it's my great pleasure to have Professor Kim here as a visitor. And today Professor Kim will give a seminar. I will give a brief introduction of Professor Kim. Professor Kim finished his bachelor, master and also PhD at the KAIST. And then after KAIST, Professor Kim started academic career in the Chonnam National University. And he has his research interest basically now in the chalk culture nanomaterials, including the castrate and also the chalk copyright, CIGS. And also for this material, they are not only used for the PV application, but also for the PEC hydrogen production, and also sensor and also energy storage. So please make Kim welcome for this talk.
Thank you, Gina. So it's very glad to have here, and then thank you for giving me the chance to present my research activities, what we are going on in, how we are doing in Korea. So I'm going to talk about our research activities and research result about CZTS thin film solar cell. So for last 7 or 8 years, we did a lot of work on these materials. So I'm going to briefly introduce about our research result about castrate thin film solar cell. First of all, I would like to thanks to all the students in my group, and then I would like to thanks to the Get Future project and the KIER, Korea Institute of Energy Research lab members, and KaiTech and DGIST, my collaborators. Okay, so I don't know how many students and researchers are here knows about Korea, but probably here most of our Asian people, so I think that knows about Korea. So the flight time from Sydney to Seoul is about 10 hours. And at this moment, now there's a Winter Olympic Games in Pyeongchang, which is about 2 hours from Seoul to Pyeongchang area. So I checked the medal list, and Australia, now they got 2 silver medals and 3 or 4 bronze medals. So anyway, I wish you could get more medals. And my university is Chonnam National University, and I'm from Gwangju City. It is about 3.5 hours by train, by bus from Seoul, which is the capital city of South Korea. And it just takes 2 hours by bullet train and 15 minutes by flight. So it is easy to access our Chonnam National University. So I wish if you have any chance to come to Korea, so I wish you can visit our Chonnam National Universities and my lab also. And our university has been established in 1952. So it has been more than 50 years, almost 60 years. And the student number is 33,000, and we have around 1,200 faculty members. So it is a kind of big university, and our university is ranked second or third among national universities in Korea. If we include all the private university, our university is ranked 10th or 11th among universities in South Korea. So our university is quite big and good universities. So we have many different colleges and graduate schools. So all the kinds of schools are in our universities, like law, medicine, business, and all different kinds of colleges are in our university. So let me show you some of our campus landscape. This is from spring season, and this is winter season scenery. So we have snow. So in Korea, we have a very cold winter season. Sometimes it goes up down to minus 15 or 20. So we have this snow season. And during spring again and summer, so our campus has a nice view. Okay, so let's go move on to the technical things. So my talk will be 3 topics today. First, I will briefly overview about photovoltaic technical evolution, and second part will be introduction of research activities in our lab. And third one will be what kind of technology issues we have to solve to increase our cell efficiencies. So I don't know how long it will take, but anyway, I will try to finish all these issues within 15 minutes. Yeah, probably. Okay, so I think you know about the global warming effect. These two photos were taken at the same place, just different in time. So this was taken in 1928. This was taken in 2004. So in like 70 years, the atmosphere changed dramatically. So these two photos were taken during summer season. In this photo, you see the glacier, but you cannot see any glacier in these photos. That means because of the global warming effect, all the glacier disappeared and only water left. So that is the effect of global warming effect. So now it is because of carbon dioxide. So now many people are working and many people are interested in new and renewable energy resources to not to use fossil fuel to minimize global warming effect. So this view graph shows that how much energy we can get from new and renewable energy resources from the nature. So you can see this small cube. This small cube shows the amount of global annual energy consumption in the world. And this big yellow cube shows that annual solar irradiation to the Earth. That means if we compare the volume of this cube and this small cube, we can see that there are 1,000 times difference between this one and this big one. That means if we can utilize the solar energy from the sun, we can only utilize like 1% of solar energy. Then we can replace all the fossil fuel to make energies, which is needed in Earth. So that's the reason why many people are working on solar energy things. So there are three different kinds of solar energy we can use. First one, we can use solar thermal. So we can use the heat directly from the sun. And second one will be photovoltaic, which is what I'm going to talk today. And the third one is artificial photosynthesis. That means we can split water and we can generate hydrogen using solar power. So these two, photovoltaic and artificial photosynthesis, are research area which I am working on at this moment. But I'm mainly focused on this photovoltaic today. So I think most of the people are here already see this kind of the slide. So last year, during 2016, at least 75 gigawatt solar PV capacity was added in the worldwide. That means, which is equivalent to installation more than 31,000 solar modules per hour. So that means a lot of solar modules were installed around the world. And maybe it hasn't been collected properly yet, but last year, 79 gigawatt solar module has been installed, and then according to forecast, maybe more than 100 gigawatt will be installed in 2021. So that means we have a lot of chance to install many solar modules on the world. That means we have a lot of opportunities to do research and to develop the technology in this photovoltaic research area. So I think this view graph you already saw many times. Then there are many different kinds of the solar cells, and the leading solar cell is now silicon solar cell, and the material system what we are interested in is casterite, CZTS thin film solar cell. The highest cell efficiency from silicon is 26.6% at this moment. And the CIGS thin film solar cell, which is a inorganic thin film solar cell, shows a 22.6% cell efficiency. Compared to those two solar cells, the cell efficiency of a castorized thin film solar cell is less, like 12.6%. This is the highest cell efficiency from castorized thin film solar cell. But there is a reason why we want to working on this CZTS thin film solar cell. So there are many economic technical issues. We want to use low cost and eco-friendly process with a high cell efficiencies. As I said, CIGS shows the high cell efficiency in 22.6%, and cadmium telluride also shows that high cell efficiency, 22.1%. But these two materials has a toxic element like cadmium and copper. In this CIGS, it has indium and gallium, which are very expensive elements. So there are a kind of a demand to replace this cadmium or indium gallium with cheap or earth-friendly, eco-friendly materials. The copper, zinc, tin, sulfo-selenized will be one of the candidate for those materials. So we can replace indium and gallium with zinc and tin. And the physical properties of this CZTS is almost similar to CIGS. Actually, if we, based on the theoretical calculation, the highest cell efficiency of CZTS is slightly higher than CIGS. The difference is 1 or 2% cell efficiency. So that's the reason why many people are working on this CZTS in recent 10 years. And let's think about the price-wise. The material cost itself, the CIGS, if we compare the material cost between CIGS and CZTS, we can see that the material cost of CZTS is almost 1/5 of CIGS. So that means if we utilize CZTS as thin film solar cell with a very high cell efficiency, then we can reduce the cost of making a module. So if we think about the PV system-wise and CIGS module-wise, to make a PV system, we need $1.8 per watt. Among them, $0.67 is for module cost. Among this module cost, $0.28 is material cost. So if we replace this absorber material with CZTS, we can reduce the production cost by 10%, the module production cost, and then we can reduce the PV system cost down to 4%. That means if we replace CIGS with CZTS, we can reduce the PV system cost by 4%. This is a lot. The manufacturing manufacturing company, the 4% is very, very big money. So that means we are very possible opportunities if we can increase the CZTS cell efficiency, which is reasonable comparable to CIGS. At this moment, even the cell efficiency of CZTS is only this much, 12.6%. But many people are working on this material, so I think we can increase that cell efficiency in near future. But as I said, this CZTS cell efficiency is still too low compared to CIGS. But if we think about history on technology development, we can see the possibility to increase our CZTS cell efficiency up to high cell efficiency. So this view graph shows that evolution of cell efficiencies in CIGS and CZTS. So the the researchers, they are working on this CIGS material from middle of 70s. It has been more than 40 years on this CIGS material. So there have been many technical issues to increase the cell efficiency of CIGS, like optimizing cadmium sulfide thickness, or band gap engineering, or double grading. So there are many technical issues that were introduced to increase the cell efficiency of CIGS thin film solar cell. But in this CZTS case, we started the research on this material in late 90s. That means it has been only 20 years. So we can also, the material system of CIGS and CZTS are quite similar. So we can introduce many technical issues which have been developed in CIGS into this CZTS system. So that means we can improve the cell efficiency of CZTS relatively easily compared to CIGS. So if you can compare this slope for this CIGS cell efficiency and with this CZTS cell efficiency, you can see that there is a dramatical change between these two line slopes. So this is because we introduce many technical issues which have been developed in CIGS into this CZTS. So maybe like in 5 or 10 years, we Castrite people hope and believe we can catch up that the cell efficiency of CIGS pretty soon. So many people are working on this CZTS material based on different preparation method of observer material. So there are many reports on nanoparticle-based observer material preparation method. This is because that it is much more easier to access. If we use this process, we don't need that expensive equipment to make an observer layer. So that's the reason why many chemist people and chemical engineering people, they're using this method to prepare the observer material, CZTS. But if we think about more commercializations, I would say that this sputtering process is much more easier to go. So there are many reports based on this sputtering process also. So now at this moment I'm mainly working on this sputtering based process. So we will discuss about this sputtering based process. So far there are many, as I explained, that many groups who are working on this CZTS thin film solar cell. In China, in Jilin University, they reported 11.5% cell efficiency based on sputtering machine, sputtering process. And Nankai University also reported high cell efficiencies. And actually this IBM group, they reported a highest cell efficiency of 12.6%, which is, but this is based on solution process. And they used a very toxic hydrogen solvent, which is flammable and explosive. So we cannot use this solvent material for the commercialization. But the meaning of this research result is that they showed some possibility of the CZTS material itself. So we could improve that cell efficiency using this CZTS material. So actually this cell efficiency was achieved in 2014. So it has been almost more than 3 years. After that, there are not much progress on this material, but anyway, at the time, this cell efficiency was very high. So they gave some kind of insight to the Castrite peoples. We can improve cell efficiencies. And also, Iraq, they reported 11.8% cell efficiency based on sputtering machine. And this UNSW SPREE group, they reported 11.5% cell efficiency. The meaning of this report is they just used sulfide-based system. If we use selenium, so if we use both sulfur and selenium together, it is easier to increase cell efficiency. But in here, UNSW, they just use sulfur only. So I think they have much room to increase cell efficiency if they add selenium in it. So I'm very happy to have a chance to collaborate with this group here. So probably pretty soon we will increase our cell efficiency. So, and so this is the cell efficiency. What is it? Solar cell efficiency report. The reported by Martin Green like quarterly, or I think yearly. Okay, by yearly. So this was reported last year, and based on this report, there are two leading cell efficiencies. First one is CZTSS, which was from IBM. Second one is from from UNSW. So I would say that IBM and UNSW is kind of a leading group in this Cassiterite thin film solar cell. But now IBM, they don't do this work that much because the leading researcher at IBM was David Mitch, but he moved to other universities. So now the research activities in CZTS is not that active in IBM. So maybe Gina's group, and let me tell you some other groups in Korea. So there are many research groups who are working on this CZTS material. One of the leading groups is DGIST. They reported 12.3%. Actually, in-house they have 13.7%, but which is a world record. But it cannot be certificated. But anyway, 12.3% they reported this is the highest cell efficiency based on sputtering process. And also there are other groups, and our university also reported 11.8% cell efficiency, which is maybe second highest cell efficiency, and this is certified by KIER, Korea Institute of Energy Research. But the result of this has not published yet, but soon I wish we can publish it. And based on published one, we have 9.2% cell efficiency in green chemistry. So this is a soft annealing process optimization things. So maybe DGIST and Gina's group and our university might be the leading CZTS thin film solar cell research groups based on sputtering process. So we'll see. Okay, now let's move on to the research activities in our group. So there are many different ways to prepare observer material. To make this kind of polycrystalline observer layer, we have to prepare precursor first. So after preparing this precursor, we have to do annealing process. So we call this is a two-step process. First, making precursor, and second crystallization. During this crystallization process, we add sulfur or selenium in the annealing atmosphere. So from this metallic precursor or sulfide included precursor, we can make CZTS or CZTSSe polycrystalline observer material. So long time back, we also did the electrode deposition, but now we are much more focused on sputtering process. To prepare the precursor layer, we are preparing this stacked layer, and then sulfo-selenization process. Finally, we have this polycrystalline thin film observer material. So to do that, we use this sputtering machine, and we make this stacked layer. So we put zinc first and tin and copper, and do sulfo-selenization process using RTP machine. And then finally, we have this kind of absorber layer. But to do that, there are many technical issues to optimize. So I cannot explain in details. But as I explained, we have to make each single layer. So we have to make a copper layer, zinc layer, and tin layer to mix them very uniformly when we anneal them. So it is better to make uniform and dense each layers. To make that each layer, we have to optimize the sputtering process. So initially, this is like 5 or 6 years back, we could make a copper layer very nicely, dense and uniform thickness, but zinc very porous. But in this tin, there is big difference in the size. So we have to optimize to make good each single layer. So we change the pressure, power, target to the substrate distance, many things. And finally, we could make this copper layer, tin layer, zinc layer a relatively uniform and dense microstructure. So we have this stacked triple layer, and after sulfo-selenization process, we could have this CZTS absorber material. So after making this absorber material, so it means that after this RTP, rapid thermal annealing or rapid thermal processing, we do use both words. So after this RTP process, we have to put this buffer layer using chemical batch deposition process, and then we have to put window layer. So, and then we have to put the top electrode material. After this, we can make a cell. That means there are so many steps to make one cell. That means if we have something wrong in one of any step, then we cannot get the cell properly. So we have to make the cell again. So we need a lot of experiment. So I really, thanks to my students, and also I think Gina also really thanks to her group members to improve cell efficiencies. And this is a photo images of our samples. For this, after making precursor, and we do sulfo-selenization process, and we put CDS on it, and then we put the window layer and top electrode material. And so we have these two different types of grid morphology. And this is a cross-sectional image of cell structure. You can clearly see that the glass substrate, molybdenum back contact, absorber layer, and very thin buffer layer, and window layer, and aluminum top electrode. So very nicely looking. But if we measure the cell efficiency, it gives 0.78%. Very poor. That means even though we have a very nice observer morphology, that doesn't guarantee you have a very nice cell efficiency. So to improve the cell efficiency, there are many technical issues. So basically, to make the solar cell, I would say there are 3 main steps. First thing is precursor preparation. In this step, we have to control the thickness of each layer to control the composition ratio of metal. And second step is sulfo-selenization process. To have nice and uniform absorber layer, we have to optimize the sulfo-selenization process, like control the amount of sulfur and selenium, or the pressure, or ramp rate, or the annealing temperature. And there are many things as I summarized here. So duration, time, many things. After that, we have to put many other layers, buffer, tissue, aluminum, and each layer, the physical property of each layer should be optimized to get high cell efficiencies. So many steps. So we have to do a lot of experiment to optimize it. And in recent 5 years in our lab, we increased our cell efficiency from 0.6% cell efficiency up to 11.8% in last 5 years. So in the beginning, we started to pure sulfide, and we also used the sulfide target. We use the zinc sulfide and tin sulfide and copper, so 3 different targets. But somehow we have many difficulties in improving cell efficiencies. So we changed the target, and we also put the sulfur and selenium together. So we could improve our cell efficiency up to 11.8%. And there are many technical issues that we introduced in during the cell fabrication process. So like heating temperature change and annealing pressure control and cadmium sulfide buffer layer optimization and to control the uniformity. So there are many issues that we introduced to improve our cell efficiency during last 5 years. So to introduce sulfur in observer layer, first we use hydrogen sulfur gas, but we couldn't control uniformity of observer layer. So we changed to sulfur powder rather than use hydrogen sulfur gas. So and many things. So we could achieve last year 11.8%. If we think about whole things, I can say there are 3 main issues that we did to improve our cell efficiency. Maybe my file size is too big. So the first step will be we have to make a reproducible annealing process. And second step will be introducing soft annealing process. And third step is controlling annealing pressure. I think these 3 things are main issues in our lab to improve our cell efficiencies. So to do this annealing process with very good reproducibility, the first thing what we did is we changed the furnace. Initially, we used the tube RTP furnace, this tube type RTA equipment. So from this tube type, we changed to a chamber type RTP process. So by changing this furnace, we could control the annealing parameters much more easily, and we could make the samples more uniformly. Like we could control the process pressure and sulfo-selenium powder ratio and uniform film morphology. So this is one step to changing our cell efficiency dramatically. So after the changing that the chamber type, we changed the sulfur over sulfur plus selenium ratio, and we changed the annealing temperature and annealing time, and so there are many process parameters to optimize the annealing process. Also, by changing the chamber, the furnace type from tube to chamber, we could improve the size of the annealing atmosphere. So when we use the turbo furnace, we use a small graphite box, like 3 centimeter by 8 centimeter. But after using chamber type, we could improve the graphite box. It's 11.5 by 11.6. That means we have much better uniformity during the annealing process. So I think this make us much easier to control the annealing process. By changing this one, we could improve our cell efficiency up to around 8%. So I will just skip this one. After that, second step is introducing soft annealing process. So before this soft annealing process, we just anneal the sample directly to the desired annealing temperature, and then hold the sample certain time and cool down to room temperature. But from the previous reports, we learned that it is better to introduce soft annealing process to intermixing precursor layer to form alloy. So that is a kind of a necessary process to avoid the loss of elements, mainly tin loss. So we introduce a soft annealing process like this. So we vary the temperature from 200 to 500, and we hold at this temperature from 10 minutes to 60 minutes, and then see how does the result changes. And this is as a deposited sample microstructure, cross-sectional SEM image, and we see 3 layers. And then after soft annealing process, we have intermixed and more dense microstructure. So this is the X-ray result after soft annealing process, and then after sulfo-selenization process. You can see that this is a precursor, but with increasing the soft annealing temperature, you see there is the formation of alloy, mainly copper tin and copper zinc alloy. But even though we anneal the soft anneal the samples up to 500, we observe that there is a tin left. But anyway, we form copper tin and copper zinc alloy. So we could form alloy, and after this pre-annealing process, we form CZTS thin film observer layer without a big secondary phase based on this X-ray result. But there are many secondary phases in real. There are 2 issues. If we anneal pre-anneal the sample at high temperature, like 400 and 500, we see the ununiform surface morphology. So this is pre-annealed at 400. You see the big change in microstructure from one area to the other area. And at 500, the difference becomes more worse. So and let me see. Okay, this is the result after the cross-sectional SEM images of the cell structure after sulfo-selenization, and we've made after sulfo-selenization, and we just observed the observer material, and we cannot see big difference in the sample pre-annealed in 200, 300, and 400 sample. But at 500 sample, the morphology becomes very worse. So, and we also made a thin film solar cell using this observer layer, and we get this result. So, without sulfo-selenization, we don't have this without free heat treatment samples here. But at 200, we have 5%. 300, we have 6.2%. At 400 pre-annealed sample, we have 6%. And at pre-annealed at 500, we have 3.2%. So we did many experiments this set. So mainly we have a better result at 300 samples. So after that, we fixed the pre-annealing temperature at 300. And so we compared what is the main reason between soft annealing process and without soft annealing process. We see that this black one is without soft annealing process, and this one is with a soft annealing process. We see that there is a, even though this is a very short minority charge carrier lifetime, there is a difference between them. So 0.3 nanosecond and 0.4 nanosecond. So because of, we think that this, because of this minority charge carrier lifetime difference, we could have high EQE value at long wavelengths, and this makes this gives that high current density in pre-annealed samples. That gives a 9.2% cell efficiency compared with 7.7%, which has not been pre-annealed samples. Okay, and the third one will be the partial pressure controlling during the sulfo-selenization process. So there are many chances for like sulfur and selenium evaporation and the tin loss during the sulfo-selenization process, because the graphite box lid is not fully fixed. So if there is a room here, it is easy to escape these gases to the chamber. So that means the atmosphere in this graphite box will be different depending on outside pressure. So we try to change the outside pressure and to see what's the difference between low outside pressure and high outside pressure. So we try to change the outside pressure from 400 to 700 total, and we don't see that much difference in the microstructure. And so in cross-sectional images, we also don't see that much difference in the microstructure. But if we look at this composition ratio, because we can see that at 500 total samples, the zinc over tin ratio is relatively uniform throughout the whole film observer layer compared to these three samples. Okay, so we want to keep the composition as uniform as we can in the observer layer because that is important. So the cell efficiency cell result shows that the sample at kept at 500 total shows the highest cell efficiency compared with the other 400, 600, 700 pressurized samples. So by tuning the partial pressure during the sulfo-selenization process, we could get a better result at 500 total samples. Actually, this result has not published yet, so we submitted the manuscript, but we will see how it will come out. Anyway, the EQE curve also shows that 500 total sample shows the best EQE result, and the TLPL result also shows that the 500 total sample shows the longest the minority charge carrier lifetime result. So I think these are all related to the better our cell efficiency result. Okay, so by controlling the sulfo-selenization process, I mean the initial pressure inside the chamber, we can change the cell efficiency. So we believe that there is a certain initial pressure when we do sulfo-selenization process. Okay. And after that, we try to control the cadmium sulfide buffer layer. So this layer, and this is a very thin layer here, just above the observer layer. So to do that, first we fix the temperature as actually we did 80 degree first, but I will show you the result about 60 degree. At 60 degree, we change the deposition time from 14 to 20 minutes. And it gives the thickness difference of CDS layer from 26 nanometer to almost 50 nanometer. So by varying the deposition time, we can vary the buffer layer thickness. And the buffer layer, the TM result shows that the buffer layer gives a very relatively nice coverage on observer layer, even though the observer layer has some like fluctuation, rough surface morphology. But anyway, we could almost continuously cover the observer layer, even though we have very thin, that is about 25 to 30 nanometer. When we deposit at during 14 minutes, the buffer layer thickness is about 25 to 30 nanometer. Even such a thin layer, we could form a very continuous coverage on observer layer. And so the cell efficiency on those four different samples shows that we have highest cell efficiency in this very thin layer. So at this time, we conclude that if we can get very thin layer, we can have a higher cell efficiency because when we check this optical transmittance, we saw that with decreasing buffer layer thickness, we could improve the transmittance of very short wavelengths region. That means we could get more light into observer layer. So that gives more photon generation like charge carrier. And also in the long wavelengths, also if we could reduce the thickness of a buffer layer, generally the buffer layer has oxygen or hydrogen oxide, which is very harmful for long wavelengths. So if we decrease the thickness of a buffer layer, we could minimize the amount of oxygen hydrogen. That means that we can get much more long wavelengths light into the observer. That gives more photon generation charge carrier. So I think that is the reason why we could have high cell efficiency in very thin buffer layer. But there are some things that we have to think about JSC and VOC together. So if we decrease the buffer layer thickness, we lose VOC, even though we could improve JSC. So so far we believe that there is a certain kind of optimal thickness in buffer layer. I would say there is around 30 to 35 nanometer thickness. So we have to do more fine tuning on this buffer layer to get reasonably good VOC and reasonably good JSC. So this is the result we deposited at 80 degrees C. By increasing the deposition time, we have the EQE, but the result shows that by increasing the VOC, we have a higher cell efficiency. But of course, there is if we increase the very large, we also lose the cell efficiency. So that means this result also shows that there is some optimum buffer layer thickness. So now we are trying to focus on deposition at 60 degree rather than 80 degree. And for our experience, we could have a more dense structure, buffer layer structure, if we deposit a buffer layer at 60 degree, and it is easier to control the thickness. So we are focused on the buffer layer deposition at 60 degrees. So by doing first things, we add selenium, and we could improve the cell efficiency dramatically because of the long wavelength, the absorption. And then after that, we control the partial pressure, so we could improve more. And then we control the TDS buffer layer, and we could improve the EQE at short wavelengths. So I think that these three things are main issues that we introduced to improve cell efficiency so far in our lab. And after making these small cells, we try to make a sub-module. So we made a sub-module 5 by 5 square centimeter sub-module, and we did the P1, P2, P3 scribe to make a module, and these SEM images of after P1 scribing, P2 scribing, P3 scribing. So, and this is the optical micrograph during the process. So precursor, after soft annealing process, we have very uniform morphology, and after the annealing, also we have very uniform buffer layer, zinc oxide formation, and after the aziel and aluminum grid, we have very uniform morphologies up to 5 by square centimeter samples. And of course, the module efficiency is very low because it has a very big cell. It is a very big cell. So, but by controlling the number of cells, we can control the VOC, and also we can control the JSC. Anyway, by controlling number of cells in sub-module, we could control VOC and JSC and power. So after that, using this sub-module, we made this small things and oops, maybe, oh, it's not working in this mode, so I'll just skip. So that windmill, actually not windmill here, the photovoltaic mill operates very well. Okay. So this is so far our best cell result. We have 11.8% cell efficiency with the fill factor of 65 around, and then VOC is 480. But if we look at the cross-sectional image of this sample, we have very ugly. So you can see there is two distinct from this to here. This is the observer layer, but you can see that the bottom layer and top layer. That means we don't have a uniform observer layer at this moment. So if we look at the composition distribution using the STEM-HAADF elemental mapping result, we can see that there is a thin zinc-rich area in that bottom observer layer. That means there are many secondary phases of zinc-related material. And also, if we see the STEM-HAADF line scan data, we see that in this bottom layer, we have a copper poor, zinc rich, and tin poor. And also, you saw that there are many voids. And also, we can see that the composition of each element, even within the upper observer layer, is not that very uniform. There is some elemental fluctuation in the observer material itself. So that means we have a room for improving our observer material. So we will, we have to do many technical development, and actually there are many issues. To improve cell efficiency, we have to improve VOC, and we have to improve JSC, and we have to improve fill factor. To do that, there are different ways. So, in next slide, I will show you the comparison between the Shockley quartz limit of CZTSSe, and this is our result. And this is IBM result. So if we compare the cell parameters like VOC, JSC, fill factor, and efficiency, our result is, in case VOC, our result is about 60% of Shockley quartz limit. That means we have a 40% room to improve our VOC. Okay? So to improve compared to VOC, like JSCC is very kind of high. Fill factor is also relatively high. So the cell efficiency is low. That means that if we improve VOC, we can improve our cell efficiency very dramatically. So for castrate people, we are having problem in VOC deficit. VOC deficit is defined as the band gap energy, the VOC voltage of band gap energy minus the open circuit voltage that we get from the cell. So far in CZTS material, VOC deficit is around 800. And CZTSSe, the VOC deficit is around 600. And CZTSE, the VOC deficit is about 580. So, castrate people, we want to minimize this VOC deficit as possible as we can. So, to do that, many people are working on. Actually, in case of crystalline silicon, the VOC deficit is very low, like 360, and gallium arsenide, the VOC deficit is around 300. So compare this well-developed material, the VOC deficit of castrate material is very, very bad, very high. So if we minimize this VOC deficit, that means we can improve the cell efficiency very dramatically. So far, in CZTSSe, the minimum VOC deficit value is 580. This was reported by DGIST, not from the 12.3% cell efficiency, but from different sample, 11.8% cell efficiency. No, sorry. This is 525. This is a minimum VOC deficit from DGIST. This is our result. Our VOC deficit is 580. That means we still have a lot of room to minimize VOC deficit. That means we can increase the VOC deficit, the VOC a lot. So for the origin of VOC deficit, these two things are two major things. first at the interface, and second thing is defect. So there are two interfaces in solar cell. First one is absorber, the interface between absorber and buffer, and second one is interface between absorber and moly back contact. So if we optimize the interfacial state between these two interfaces, we can minimize the VOC deficit. And also the other things, if we decrease the bulk defect and decrease grain boundaries by increasing grain size, and if we minimize the secondary phases by optimizing the sulfo-selenization process, that means we can decrease the VOC deficit. So there are many ways to do it. So if we think about observer buffer layer interface, we can do this kind of things. For observer layer, we can do this kind of many different things. And for observer back contact interface, we can do different kind of treatment. So we still have many things to do to improve the VOC deficit. So recently, one group in Henan University, Sichin Woo, they tried to decrease the VOC deficit by doping silver elements into observer material. So by doping silver into observer material, they said that they can increase grain size. That means they decrease the grain boundaries. And then they can reduce cation disorder. So copper in zinc site. This is a very gives a very detrimental effect on VOC deficit. So they could improve a VOC deficit a lot by introducing silver into observer layer. So, but their process was based on a solution process. So we tried to dope silver into our system by sputtering based process. So we deposit silver on these pre-stacked precursors using e-beam evaporation method. We change the thickness of silver and then observe the morphology changes. As you can see, this is without silver, and this is with silver 30 nanometer thickness. You can see that there is a dramatic change in the size of grain, right? So by introducing silver, we have a very large grain size. You can see that on plan view, and you can see that in also the cross-sectional view. But even though we could improve the grain size, the cell efficiency didn't go high. So this is without silver, and other things with the silver. So we thought that what's the reason why we could improve our cell efficiencies? And we figured out that we are doping silver to replace copper. That means if we want to dope silver, we have to reduce the amount of copper in the original precursor material. But in the first experiment, we didn't change the amount of copper. So next set of experiment, we try to change the amount of copper in this precursor layer. So we varied the deposition time for copper layer and fixed the silver layer at with 20 nanometer, and see that this kind of change. This is without changing copper layer thickness, and this is with changing copper layer thickness. We put silver layer 20 nanometer same. So you see there is a big difference. So without changing copper layer thickness, we have worse cell efficiency, worse cell parameters. But with changing copper, the amount of copper, we have comparable the cell efficiencies. That means if we do more fine tuning on copper and silver layer, then we believe that we can have a better efficiency, and we could have a low VOC deficit eventually. So we are working on this, and also we are working on several different ways to minimize the VOC deficit at this moment. Okay, so far we have achieved 11.8 CZTS thin film solar cell without additional treatment to minimize the VOC deficit. So if we introduce some kind of method to minimize the VOC deficit, I believe that we could improve cell efficiency and we could have world best cell efficiency in near future. So let's get together. Okay, so if you visit pvsolar.chonnam.ac.kr, you can see what kind of facilities and what kind of publications and who are in our group. So you can check all those information by visiting this pvsolar.chonnam.ac.kr. Okay, thank you very much for your attention.
Very generous sharing with us about the step change key technologies from the efficiency of less than 5% to 11.8%. I have learned a lot, but due to the limit of the time, I can only accept one short question. Any our team has it. I have tons of questions. I can ask Professor Kim later on. Do you guys have any questions?
I have one question. Where you get the silver layer on the top?
Silver layer by E-beam evaporation. Yeah, E-beam evaporation.
Okay, so I believe you guys have one question too.
Yeah.
But we can gather time later. So let's thank Professor Kim again for the excellent talk.
Thank you very much.